Uh, 2023 Mechanical Metallurgy. The magnitude of the Berger vector of the dislocation resulting from the reaction of the dislocations A by 2 101 and A by 2 1 bar is A by 2 101 and plus A by 2 1 bar is equal to A by 2 into 1 bar 0. So if you see the magnitude of the dislocation resulting from the reaction, you get A by 2 into root over 1 square plus 1 square plus 0, which is equal to A by 2 into root 2. So this is equal to A by root 2. This is the answer. The mechanism of the creep of a single crystal is depicted in the schematic. If you'll see, the nebara is a deformation in the process in a crystalline material at high temperature due to atomic diffusions within the crystal lattice. Here, the atoms are moving in this way and the vacancies are moving in this way. The factor which affect, so the answer is never having. The factor which affects the never are diffusion at elevated temperature, atom move between the lattice sites through vacancies and the interstitial position, activation energy. The energy required for the atoms to overcome barriers to move is called activation energy, and the stress enhanced diffusion. External stress aids atomic diffusion by providing additional energy to overcome barriers. Significance seen in the high temperature environments, aerospace materials, furnaces. It is also important for the material design in such conditions. So it is dominant at lower stresses and higher temperature. The dislocation creep becomes more significant at higher stresses, influenced by the factors like grain boundaries, vacancies, and dislocation density. Okay, and never contributes to the deformation at higher temperature due to the atomic diffusion and the atoms affecting the material behavior and the design of the high temperature applications. If you see, the strain rate of a never herring is given by 2d sigma b cube by alpha d square bf kt. So it depends on temperature, it depends on stress you are applying, depends on temperature, Berger vector, etc. and the grain size of the material also. When the crack propagates in the brittle materials, you'll see the elastic energy of the material decreases and surface energy of the material increases because the during a crack propagation in a brittle material, when you apply the stress, you will see that the crack propagation involves the formation of a new surfaces. So new surface means breaking of more number of bonds. As the surface energy has more energy, breaking of more bonds increases the surface energy of the material as more number of bonds are being broken. So surface energy increases and the elastic strain energy decreases because the presence of crack causes local redistribution of the stresses within the material. As the crop propagates, it creates a new crack surfaces. The material enhance the release of the elastic strain energy, and this strain energy is stored in the material due to deformation caused by applied loads. As the crack grows, the deformation region ahead of the crack relaxes, and the stored elastic energy, whatever is there, will get decreased. So it's not this one. And for the in brittle materials, it is given by Griffith theory of fracture, where sigma is equal to 2e gamma by pi c, where surface energy in the crack growth. When a dislocation a loop of PQ RSDU in 111 plane of a cubic single crystal with a Berger vector of 1 by 6, 1 bar to 1 bar, the dislocation segment PU bar and PQ bar are parallel to 0, 0, 1 bar and 1 bar 0. So the Berger vector is given, it is parallel to 1 bar to 1 bar. So it lies in the plane of 111 Uh, so if you'll see here, PQ, PUR and PU bar, if you'll join these two dislocation, this dislocation join to form these dislocations. These two partials join to form this dislocation. This line is parallel to it. So if you'll combine PU bar plus PQ bar, you get 0 1 bar 1 plus 1 1 bar 0. You get 1 2 bar 1. And if you will check for the angle between them, these two are parallel. So Berger vector and this is parallel. So and this is parallel. So the Berger vector is parallel to U2. So it has a screw character. And now if you see the Berger vector angle between Berger vector and the dislocations, 1 bar, 1, 2 bar, 1, 2, 1 bar into 0, 1 bar 1. So the cos theta between them is 1 bar plus 2 bar by root 2 into root 6 and 1 bar to 1 bar into 1 bar 0, which is equal to 1 bar plus 2 bar by root 6 into root 2, which is equal to 3 by root 2. So it is root 3 by 2, root 3 by 2 minus minus. So the angle between them will be cos theta of uh, 120 degrees and 120 degrees because it is minus root 3 by 2. So PU bar and PQ bar has mixed characters. And the QR is not an edge character because QR is parallel to the Berger vector. Parallel to the Berger vector, the dislocation segment will be screw dislocation. A thin plate is loaded in a plane stress condition with sigma xs equal to 110 MPa and sigma yy is equal to minus 50 MPa. Tau xy is minus 70 MPa. The maximum principal stress is given by sigma xx plus sigma yy by 2 plus root over sigma xx minus sigma yy by 2 whole square plus tau xy square. This is equal to 110 minus 50 by 2 plus root over 110 plus 50 by 2 whole square and minus 70 whole square. So it is 110 minus 50 is 60 by 2, it is 30 plus root over it is 160 by 2, it is 80 square plus 70 square, which gives you nearly 136. Thank you. The strain hardening behavior of an alloy is given by sigma is equal to 1100 epsilon power 0.3. The true stress and true strain are respectively. So it is given that the reduction in area is A naught minus AI by A naught is equal to 0.1%. Then A naught by AI is equal to um, point 1 by point 1. So it is 1 by point 9. A naught by A1. So, reduction in surface, reduction in the area is cross-sectional area is nothing but the strain. It is ln A naught by A in final, which is equal to ln 1 by 0.9 is equal to 0.105. This is the strain due to reduction in area. Uh, and the unknown strain amounts. At the maximum load, the strain is nothing but 0.3. So this maximum strain is nothing but sum of unknown strain plus strain due to reduction in surface area, which is equal to 0.105 plus x is equal to 0.3. So x is equal to 0.195. Which of the following is responsible for reducing the high cycle fatigue life of a component? If you see, the increase in mean stress at constant amplitude also reduces the fatigue life, and also increasing the surface area will reduce employing short pinning and absence of sharp corners. So the answer is this and this. Because if you see increase in the mean stress at a constant amplitude, the high cycle fatigue refers to the fatigue failure that occurs under relatively low stress amplitude and a large number of loading cycles. So the mean stress, which is the average stress during the cyclic loading, plays a significant role in reducing the fatigue life of a component. When the mean stress is increased while keeping the stress amplitude constant, it results in a reduction of fatigue life. The increased mean stress causes higher levels of tensile and compressive stresses in the material during loading cycling. These alternating stresses can promote the crack initiation and accelerate the crack growth in the material. So, the alternating stresses lead to the premature fatigue failure of the component. Increase in surface roughness. The surface roughness of a component also affects the fatigue life of the component. When the surface roughness increases, it introduces stress concentration and microstructural discontinuities in the material, and this accelerates the crack initiation and crack growth, ultimately leading to premature fatigue failure. Employing short pinning, so if these are the cracks present on the surface, when you introduce short pinning, that is the technique that can actually enhance the uh, high cycle fatigue, involves the bombarding of the surface with small spherical particles called shots to introduce compressive residual stresses and create a layer of compressively stressed material. So it can counteract the tensile stresses that promote the crack initiation, thereby increasing the component resistance to fatigue failure, and the cracks which are present near to the surface will get closed here. Absence of sharp corners. The presence of sharp corners also contribute to the stress concentration, which might be detrimental to the fatigue strength. So, however, absence of cannot also guarantee an improvement in fatigue life. So, absence of sharp corner also uh, does not guarantee increase the high cycle, but it can help to not increase it. A specimen containing maximum surface crack of 1.5 mm, which cyclic loading of sigma max 300, and so if you'll see here, it is given as delta k equal to sigma max minus sigma min by root over pi a. So both are tensile stresses, then you'll take the sigma max minus sigma min. Whenever compressive stresses are there, you'll neglect this sigma minimum or whatever is given. So you have 300 into root over pi into A is given as 1.5 because as it is given as surface crack. So directly A is equal to 1.5 into 10 power minus 3. So the value which you get is 20, nearly 20 MPa meter power 1 by 2. And R is given as sigma min by sigma max, which is 0 by 300. So 0. So for R0 and delta K 20, you need to find the value of dA by dN, which is equal to 10. So the answer is 10. Thank you.